morning and welcome to our third webinar about simulation. This new session is dedicated to the magnetic pulse welding processes. My name is Tabata and I am a member of the marketing team at Bmax. During the next 45 minutes, you will meet Gilles Mazars, the head of the simulation department at Bmax, and he will present a few case studies to demonstrate our approach and expertise. As usual, if you have any questions, you can submit it directly in the private chat box located at the right of your screen. And if you are on a mobile version, you can find it directly on the bottom of your screen. Gilles will provide with answers at the end of the presentation. And don't worry, if your questions were not answered, you will receive a personal response by email very soon. I'm going to turn it over to Gilles now, so I wish you all a very good webinar.
Thank you, Tabata. I'm Gilles Mazars, and welcome to this Bmax webinar about simulations. This third episode is dedicated to magnetic pulse welding, MPW. It's the fastest process in Bmax using HPP, high pulse power, because we have to generate very high loading to activate special behavior in the materials. So, after a few words about Bmax, we introduce MPW processes and applications. We describe simulation objectives and software and the special capability to design and to optimize MPW processes. We highlight the main advantages of this process, and we conclude with a detailed case studies. The first one is for battery cooling system, it's a flat welding, and the second one is cylinder welding for HVAC applications. Bmax has developed innovative processes and provides with equipment and services using high pulse power, HPP, for industrial applications. Basically, the product of Bmax is a pulse power generator. And this generator can be plugged on several devices, coil or electrode system in water, to perform any industrial manufacturing applications like forming, welding, assembling, and calibrating. In this webinar, we'll speak about only welding. There is two business cases in Bmax. The first one is to produce a component, assembly, and the second one is to deliver HPP system. To complete its offer, Bmax has any services, training, engineering, and simulation. The Bmax solution have a very small environmental footprint. They are compact, ultra-low energy consumption, there is no chemical emission and no heatings, and it's quick and repeatable. Now it's a presentation of an MPW system. There is a high pulse power generator, including a control cabinet, a capacitor banks, and a trigger named a switch. And we plug this generator on the coil. It's the final stage of the system. And in this coil, we put the workpiece, a tube, and a cap in this case. Thanks to the control cabinet, we manage the energy level, the voltage, for example, and we load the capacitor bank slowly with low power. After, we release all this electrical energy thanks to the switch. We deliver this energy very fastly in the coil. The current goes through the coil and create a magnetic field. It's the blue line. If you put a metallic part in this magnetic field, you create induced current in green. And the combination with magnetic field and induced current creates the resulting Lorentz force. And thanks to this force, we are able to weld, to form, or to crimp. To be clear in the explanation, I have to introduce any definitions. The coil, the flyer, and the anvil first. The coil, it's plugged directly to the generator. It's the electrical device which adds the direct current of the generator. It's the inductor. And we create Lorentz force on the flyer. It's a workpiece with a moving. And this flyer impacts a target, and this target is the anvil or the parent part. From the 3D model, the CAD model, we can perform a cutting view and a 2D section. And in this 2D section, we can analyze three critical, more important parameters. The working length, it's the overlap between the coil and the flyer. The magnetic gap, it's the clearance between the coil and the flyer. And the gap, it's the clearance between all the workpieces, flyer and parent part. The range of application in Bmax is quite large. We can address automotive, energy, and aerospace applications. In automotive, we can work on HVAC, on drive shaft, and for filters. We are able to weld complex shape and dissimilar materials like aluminum and copper, aluminum and steel, silver and copper, and so on. The industrialization of MPW is easier for all the materials if the conductor if the flyer is a good electrical conductor and few millimeter thick. It's a good condition to develop industrialized system easily. Simulations. It's a complex process. That's why we use simulation. The first objective of simulation is to understand physics, understand what happened, and to perform any sensitivity studies. The second point is to design and to optimize components and processes. By this way, we're able to save time and cost compared with development of a brand new prototype, for example. We use LS-DYNA software. It's a commercial code, and we developed a lot of special capabilities for data processing and user subroutines to address the specifically MPW processes. We have a service of simulations, and you can take a look on the first webinar. It's an overview of simulations capabilities and applications, and how we use simulation for all the Bmax processes. And it's a uniqueness in Bmax: material characterization, data processing, expertise in HPP, in forming, and in simulations. How we use simulations to address MPW processes. All processes in Bmax are dynamics and multiphysics. Dynamics because all the process is done in few microseconds. And multiphysics because all the process consists to convert electrical energy in mechanical energy. For magnetic pulse applications, crimping, welding, or forming, we use a coil to create Lorentz force. So the simulation software, we have to activate special capability, and we have to be dynamics and multiphysics. And by this way, we can address HPP problems. Basically, we perform a coupling between the mechanical solver, which calculates stress, strain, and the displacement in conductor in dynamics. And we plug this solver with the electromagnetic module, which updates all the electromagnetic field, like a magnetic field, electric field, and the current density, and the Lorentz force at the end. And this Lorentz force is directly used by the mechanical solver to calculate accurately the loading. In the metallic part, when we have a current induced, for example, we create heatings. And we have to perform a coupling between the thermal solver and the electromagnetic module, for example, to update the electrical conductivity. Because when the temperature increases, we have a decreasing of the Lorentz force and the efficiency of the process. That's why we perform these three coupling between the three solvers. In this example, we applied the pulse current directly on the coil, the red component on the screen, and the coil creates magnetic field and push the flat blank in the bottom of the die. The fringe, the corer, represents the maximum of Lorentz force. All the process is done in 64 microseconds. As you can see, the maximum of Lorentz force depends on space and time. That's why we perform this kind of coupling between all these solvers. MPW principles. In the history, we defined the welding window for explosive welding applications. We use two main parameters: the angle between at the impact and the contact closing velocity. The angle is defined by the clearance between the two components, and the contact closing, the speed of the contact closing, depends on the explosive material properties. The sound speed of detonation is constant, and it's exactly this speed. In magnetic pulse applications, in magnetic pulse welding, this velocity is not constant. That's why we use the component of the speeds normal to the interface, to the contact surface, VR, in red in this screen. By this way, we are able to define magnetic welding windows, the condition required to expect a welding. The drawing represents this parameter, angle and speed, and normal speed to the interface. The first limit is the yellow straight line. We have to reach high speed to activate aerodynamic behavior in the material. After this limit, when we reach this speed, we create high pressure, and this pressure is predominant, and the material is like a fluid. Thermodynamically, in terms of pressure and temperature, it's solid, in the solid state. But the hydrodynamic behavior consists to have a fluid behavior. So it's the first limit of the welding windows. The second limit is the sound speed in the materials. It's a green line. If the contact closing is too fast, we create a shock wave in the material, and the bounce back and the effect of this shock wave can destroy the welding. Even if we have a good pressure and temperature to create welding, we can destroy it due to the bounce back and the reflection of shock waves. It's the second boundary of the welding window. The third, it's the melting temperature. When we have the speed between the velocity at the impact, we can define the pressure and the temperature. And we have to be sure the temperature don't reach the melting temperature. If we reach this temperature, we have a fusion and we change the phase, and it's not solid, it becomes liquid. So this third line describes the theoretical welding window. In Bmax, we create a new welding window, numerical welding window, more accurate. We perform 2D simulation in a plane strain, and we follow the contact collision for several configurations in terms of angle and impact, velocity at impact. The blue and green point are good conditions to expect a welding, and the red point, it's when the contact closing is too fast, is with a speed higher than the sound speed in the material. As you can see, we create a shock wave, and due to the reflection of this shock wave, in the bottom of the screen, we have a blue spot, and this blue spot destroys the welding. So, thanks to this welding windows definition, we're able to describe accurately the good condition to expect a welding. After, in terms of simulation, we perform 2D simulations. You can identify the 3 critical parameters, the working length, the magnetic gap, and the gap between the workpieces. And during the simulation, we can track for each node at the interface the angle and the speed. By this way, we are able to project this data on the welding window, and we can analyze what happened during the process in function of these 3 parameters, working length, magnetic gap, and the gap. So as you can see on the A point, we have a very high angle and a good speed. We are in the middle of the welding window. After, during the process, we have a flat impact. So for a good velocity, the angle decreases and re-increase after. So in the point B, we are out of the welding window, and in C, we have a large angle at the end of the process, and we are again in the welding window. So according to this analysis, we can say we have an issue maybe on the point B. And after, we perform any test, and we can measure by micrography the length of the welding done, and we can identify where the welding is good or not with green and red colors. And we project and we transfer this data on the numerical result in the welding window. And as you can see, on the A point, we have no welding. It's normal because we have a delay. Even if we are good condition, we have a delay to create the intermetallic, for example, between dissimilar materials. After, in the process, we have a decrease of the angle, and we go out the welding window. We are in the B point, and at this point, we have no welding, as expected. After, the angle at the end of the process increase again, and we are in the C point. We have a good welding on this point. So by simulation, we can optimize any parameters like geometry, assemblies, and loadings to enhance this result. Regarding the geometry, we can optimize the coil section, for example, to increase the current density and the Lorentz force applied locally on the flyer. And we can change the parent part geometry to maximize or to change the angle at the impact. The second point to optimize is the assembly. Again, working length and the gap between the components. At the end, we can optimize the loading in terms of maximum of current, the energy level if you want, and the frequency. If the loading is too long, we have the maximum of force after the impact, so we don't create a very high impact velocity. If the loading is too fast, we don't push during the process, so it's not a good configuration to optimize the welding. So by simulation, we can change these parameters to define an optimized configuration and to enhance the welding. In this case, we change just the gap between the flyer and the parent part, and by this way, as you can see, the new path is fully in the welding windows. So this second configuration is better than the first one. We have a longer and more homogeneous welding in this case. Now we'll speak about the advantages of this process. Basically, MPW system is very high performance because we are able to weld at the solid state dissimilar material with a high-speed collision between the two metals, possibly dissimilar, at the room temperature with high repeatability. So the main advantage of MPW is to be fast, to be able to weld dissimilar materials with high performance, with no heat-affected zone, and for complex shape. It's a fast process. As I said before, all the process is done in few microseconds. On the right, we have the speed of the process in the real world, and on the left, it's what happened in simulation. We can analyze slowly what's happened during all the process at the impact to track angle, velocity, and to identify the potential issue before the prototype. After we are able to form dissimilar material. In this matrix, where it's a simple summary of a combination of metal we are able to weld or not. Basically, the flyer has to be a good electrical conductor to maximize the efficiency of the system. So that's why usually we use aluminum or copper. In terms of parent part of the anvil, the target, if you want, we can use steel, copper, aluminum. The range of material is larger. High performance. We can plan any test to measure, to evaluate the performance of the joint. For example, we perform peel test and micrography. Micrography is after the peel test. Peel test is to localize the welding and to test the strength of the joint. Micrography to measure the welded zone, for example. After, according to the functional requirement from the customer, we can perform any mechanical test, burst test, pressure, and helium, hydrogen, leakage, for example, or mechanical test like torque or tensile test. Usually, the joint is stronger than the welded materials. We are not able to join and to perform end-to-end join. We have always an overlap between the cap, between the parent part and the flyer, for example. No heat-affected zone. To perform magnetic pulse welding, we have to reach a very high velocity at the impact. By this way, we create very high pressure and high temperature very locally at the contact closing. These high temperature and high pressure generate good intermetallic for dissimilar materials, very thin, few micrometers in the thickness. By this way, we have a strong welding. But the high temperature is very local. It's just a spot and very short in time. By this way, we have no thermal transfer, thermal diffusion in the component. So the temperature at the end is very low, and we don't change the mechanical property of the materials. That's why we have no heat-affected zone. To conclude, the last advantage of MPW process is we can address different shapes. We are able to weld flat geometries and cylinder geometries and complex shape. The stakes of the Codesign is to tune the loading and to optimize the welding process. Now I will present the first case study, battery cooling system. The process is a flat welding, about two plates in copper alloy, 0.4 millimeter thick. It's a complex shape with corner and large dimension. The requirement consists to create a continuous join all around and with no leakage. So, as usual, the material identification. Here it consists in the welding windows definitions in theoric and numerically for this couple of material, copper and copper. After we perform 2D simulations, the step one, it consists to develop, to use an existing system, an existing setup, to validate the welding windows. We perform any micrography to check if the welding windows is a respect. And as you can see, the green line shows the length of the welded zone, and we are in good compliance with what we expect. After, in the step two, we define a coil section in the step 2A in red. We define a coil section, but as in the previous example, we have a critical area. The path in terms of speed and angle go out the welding windows. That's why we iterate, we change the coil section, the overlap between the workpiece, and by this way we optimize the process and we optimize the system with the coil section defined by the green area and named step 2B. After, thanks to these 2D simulations, we can calculate the temperature during the process. And we can estimate the maximum temperature in the coil in the active zone, and we can compare with the melting point. We don't want to melt the coil for sure. And for a lifetime analysis, we can estimate the temperature increasing in function of the production rate. And this data is used again to optimize the cooling system for the system. After, we perform 3D simulation, for example, to optimize the coil in the corner. Here, it's an example where we iterate on the section radius. We studied 25, 13, 40, and 45 millimeter in the radius. And we check all angle and velocity, and we project all these results in 3D in the welding windows. In this case, when we have a large radius, we have a low performance in terms of welding, and for a small radius, the smallest radius create a very small length, welded length. That's why the optimum is around of 35 millimeter in the radius. After, thanks to the 3D simulation, we can optimize the slot. The slot it's in the coil where the current go in and out. This current path disturbs the magnetic field. So by this way, we change the angle and velocity at the impact. So we use 3D simulation to check if we are again in the welding windows. It is the case with this final design. After, we validate all the design, all the CAD file, the corner and the slot with a full model of the system. And we check, as usual, the angle and velocity all around the product. After, the last stage consists to perform a refit and support to the experimental to test campaign. And we can compare the numerical and experimental results. And we have a good compliance in this case. With micrography, we can check the welded length, and we can project it on the welding windows, and we understand what's happened. It's exactly what we expected. The second case study is about HVAC production system. Bmax proposes advanced MPW solution to design and to optimize components and processes to maximize the efficiency and to minimize the scrap rate. Here, the product is a CO2 accumulator. It consists in a tube with two caps, and the flyer is a tube, and the parent part are the two caps. So it's one assembly with the welding to do. The aluminium, it's a 6082 temper T6, and the flyer has a thickness of 3.1 millimeter. The project consists to design a semi-automatized production system able to produce 350,000 assemblies per year. The requirements are about geometry, helium leakage, and there are specific functional requirements about cycling. First of all, we define the welding windows for this aluminium 6082 T6 on itself, numerically and theoretically. After, we perform 2D simulations. The first configuration consists to reproduce the configuration of an existing setup to validate experimentally the welding windows. It's the green line on the drawing. After, we design the new coil section for this application, especially for this product. And in this case, we have an optimization of the loading of the voltage. It consists of the energy level. As you can see, for each voltage, we have a new curve. The next step consists to optimize the coil section. Again, we can compare this result with the existing setup. And thanks to this simulation, we are sure we can optimize, we can have a better configuration compared with the existing setup. So after, the next step consists to perform 3D simulation and to check if we are in good condition at the slot area. Again, the slot area, it's where the current go in and out. And this path of the current disturb the magnetic field and the Lorentz force. As you can see in the drawing, the maximum Lorentz force decreased by 15%. Sorry. So by 3D simulation, we'll check speed and angle to project this data on the welding windows. In this case, we'll validate the welding windows, so we are sure in the slot area we are able to weld. So thanks to the simulation, we are able to say this coil and this HPP configuration is able to create continuous welding all around the tube. Then, thanks to simulation and the temperature analysis, we can design the cooling system. Thanks to simulation, we can calculate the temperature increase during one shot. And we can calculate the temperature during the production phase, according to the production rate, So thanks to the simulation, we can say with a water unit able to deliver 3.5 liters per minute, we need a temperature in water inlet of 12 degrees, and the temperature increase by the cooling system is a few degrees. So thanks to the simulation, we validate the HPP configuration and we design the cooling system. The next step is to build the prototype and to realize the first test. And with the first assemblies, we can check the geometry, the geometrical KPI, key point of interest. We can perform any peel test and analyze by micrography the length of the welded area. After, the customers check the helium leakage, 143 bars during 1 hour. It performs a burst pressure test, 260 bars. And the functional requirement about the cycling, it performs 150,000 cycles during 292 hours. So after the validation of all these assembly, the next step is to design the production system, to design the workflow, to validate the production rate, to design the monitoring, validate the cycling, the lifetime of components, to check the repeatability, the capability of the system, and to define the maintenance program. So at the end, we are able to deliver a production system with a production rate of 2 assemblies per minute, 4 welding per minute, with a scrap rate less than 5%. Here, it's a CAD file of the full system as designed, and the real system in the workshop ready to go in the customer plant. In conclusion, regarding MPW processes, Bmax can produce assembly or deliver industrial system, standalone or fully integrate in a production line. Thanks to simulation and specific capabilities developed internally in Bmax, like Welding Window, we save time and cost to define the best condition to weld, to limit the prototype phase, and to reduce the lead time for production. Thank you very much for your attention. Stay with us. Now we'll answer to your question with Tabata.
Thank you, Gilles, for your presentation.
You're welcome.
So this is the moment for the question and answers. We received a few questions during your presentation, and the first one is, what are the maximum dimensions that can be welded in circular and flat geometries?
Regarding circular geometries, the range of diameter is a few millimeter up to a few tenths of millimeter. It depends on the material and the thickness. For flat geometry, the welding width is few millimeters, but we can weld 2 meter long, a line 2 meter long between aluminum and steel, for example. We can weld complex shape, complex geometry. It's doable, but we have to pay the special attention on the assembly to control all the gap between the workpiece and the active zone of the coil, for example. But it's doable, and by this way, we're able to maximize the efficiency of the process and its repeatability.
Are there any limitations in terms of flyer thicknesses, and is it possible to weld foils?
Regarding the thickness, if the flyer is too thin, the Joule effect increases, so the temperature increases during the process, and we can reach the melting temperature, and we can damage the active components, so it's not good. And if the thickness is too large, we cannot accelerate the flyer, and we are not able to reach the high velocity for the impact required for the welding. So it depends again of the electrical conductivity of the flyer and of this mechanical property. Usually the skin depth in our application it's 1 millimeter. The skin depth is a penetration of the current into the materials. Mm-hmm. Okay, and we have to adapt the thickness of the flyer to this skin depth, in fact. So for 5 micrometer to 100 micrometer for foils. It could be challenging to perform a welding. And if these foils are in stainless steel, it's a bad electrical conductor, so it's not possible at the end. We have experience in foil for automotive applications. It's challenging, but you can contact us to discuss options.
Another interesting question, how long does it take to determine a welding window?
For welding window, we need few material properties. So it's for the couple of materials. Few hours are required for numerical and theoretical welding window. That's all.
Pretty fast. Okay.
Yeah.
What is the cost per weld?
The cost per weld. To give an accurate cost and accurate figures per weld, we have to consider a lot of parameters. The energy level, consumable, the HPP system required to make the job. Regarding consumable, for example, insulator in PTFE, for example, or the coating of coil or field shaper has to be changed usually between 10,000 or 100,000 shots. By this way, according to the energy level, we tune the maintenance program. But again, it depends on the application, HPP system, required energy level, production rate, and so on.
What is the amount of electricity that is necessary per weld, and what about the cost?
Yes, regarding energy, for instance, in the last case study, if we take 50 kilojoule per shoot, and if the production rate is 15 seconds for one shot, with the French price of the kilowatt-hour, 0.2 euro, we can imagine a shoot around of 0.002 euro per shot. So the cost of the energy is less of 1 euro for 1 hour of production.
What are the couples of materials that can be welded by MPW? And do you have any experience in welding titanium or titanium alloys?
Yes, as we presented before, the range of material is very, very large. And the key point to industrialize MPW system is to use a good conductor for the flyer, good electrical conductor for the flyer. After we have an experience regarding titanium and titanium alloy welded with a flyer in aluminum. There is no special limitation. It's not simple because the welding window is narrow, but we can compare with welding between aluminum and steel, for example. It's not more difficult, but it's difficult to accelerate titanium. Titanium is not a good electrical conductor. That's why we cannot use it with directly like a flyer. We have to use a driver, a pusher. It's additional material like a ring for tube geometry, for cylinder geometries. And we cannot accelerate directly a titanium, but we can weld titanium and titanium alloy.
Okay. Another question, is it possible to weld thin tube on thin tube?
Yes. It could be very tricky to weld thin tube together, thin tubes together, because MPW process requires very high impact velocity. And by this way, we create very high pressure and we can collapse the inner tube. We can crush it. So that's why it depends on the thickness of this tube, inner tube, the parent part, and the mechanical property. In steel, with few millimeters in steel and 10 millimeters in diameter, we can imagine to avoid the collapse, but after it depends on the geometrical tolerance. For opened tube, for example, opened components, for industrial solution, we can imagine to use a mandrel, an additional part inside. We perform the MPW process, and after we can remove it. So it's the best way but just for opened components.
Which parameters are monitored in industrial MPW systems?
For industrial systems, in the case studies, for example, in the second case studies, usually we check, a check is done at the start of the switch, of the shift, sorry. We control the leakage, we check the geometrical KPI, key point of interest, and we perform any peel test and micrography. After, during the production phase, the monitoring is only on the current. We check the maximum current and this frequency. There is any tolerance, and if these parameters, maximum of current and frequency, go out of this tolerance, we stop the production. And it's enough to check if we have a defect in the system or not. After, regarding the monitoring of the assembly, at the end of the process, we can use some conventional tests, non-destructive tests, for example, a conventional method, like ultrasonic, for example, to check if the welding is homogeneous, and it's non-destructive test.
What are the main advantages of MPW compared with TIG, FSW, laser welding, etc.?
Yes, MPW, it's quite different. We are able to join dissimilar materials. It's a fast process. There is no heat affected zone. It's very important because we save the mechanical property of the components of the part of the welded part. It's a repeatable process, and there is no additional material during the welding. We merge, we joined only the flyer with the parent part. After, we can reduce the post-process operations, and it's a strong welding. So to make it simple, it's fast, repeatable, and clean. And regarding the energy consumption, it's ecological.
Fast, repeatable, and clean.
Yes.
How many industrial MPW systems have been installed at customer sites?
Regarding industrial system, roughly 5 or 6 production systems in North America, 5 in Europe, including 2 in France and 3 in Asia.
3 in Asia, yes. And we are working on standardizations
exactly.
to increase this number of production systems
sure.
in the world.
Yes, exactly. And in addition, we can produce in Bmax. Internally, we can produce assemblies internally in Bmax plant.
So what is the maximum production capacity of an MPW system, and what is the total time required per weld?
It depends on the assembly. In the case studies, we are around of 15 seconds per shot for a diameter of 80 millimeters, for example. But if you change the diameter, if the welding is easier, we can reduce the energy level and you can enhance the production rate, for example. And we can shoot 7 seconds can be required for one shoot. So if we integrate on 1 year, so we can perform 1 million shots in 1 year with one system. So it's an order of magnitude.
The production capability can exceed 1 million shots per year for one system. That's what you say.
Yes, exactly. For the fast process, the fastest process, and for one machine. Yes, exactly.
Okay. Is it necessary to clean or degrease parts before MPW?
Not really, because during the process we create a jet, and we can remove all dirty or we clean during the process. So it's not useful sometimes to clean the surface during the welding. It could be an advantage of this process. It could be an advantage, yes, for this process. So it's a small dirt, so not necessary to clean.
We will finish with 2 other questions. So the next one is, what is the cost of an MPW system? And I can answer to this question and say that the cost of MPW system depends on options and capabilities to integrate. So you are free to contact us if you have any questions about these specific subjects. Gilles, what is the lead time for an MPW system?
The lead time for production was, in the past, it was 18 months. Today, we are able to deliver a system in 12 months. And thanks to the standardization, we want to reduce this lead time to around of 8 months.
The last one?
Yeah.
Can Bmax help co-design products with its customers?
Yes, of course. Yes, it's better. It's the best way to enjoy of all the benefits of MPW and to maximize the efficiency of the system for the final product. In Bmax, we have expert and the design office can help you to develop an efficient and robust assembly. So sure, the Codesign is the best way.
Thank you, Gilles. Thank you for your time. Thank you for your presentation.
Thank you very much.
This new session is almost closed now. We hope you enjoyed it. If you have questions or needs regarding specific applications, don't hesitate to suggest your topics for the next webinars. As I said at the beginning of the session, don't worry if your questions were not answered. You will receive a personal response by email very soon. The next webinar will take place in the coming months, so stay tuned to our social medias and our website to get more information about it. If you have 2 minutes left, please complete the survey that will appear in a few seconds on your screens. It will help us improve our future webinars. Thank you very much. Thank you again for your participation, and we hope to see you again.